Okay, here is the case 2, another situation. Well, we have the same beam segment subjected to the same bending moment couples as the case 1. But in this case, the cross section is composed of a cap and a rib. Okay, this is different from the previous case, where we have two side ribs, two side flanges, and a central rib. Okay, so here in this case, we're determining the shear stress on the interface between the cap and the rib, as denoted by the green colored interface in this figure. Okay, we can follow the same procedures as in case 1 to calculate the shear stress here. Okay, so first of all, the Y bar, the cross section is shown below. Then the Y bar is actually the same as the case 1, right? The Y bar is 4.43 inch. This is from the top to the centroid. Right? Here is 4.43 inch. Then the I will also be the same. That is 346.5 inch to the fourth. Then I can say that the stress will also be the same, right? If we still cut off the we cut off the cap. Okay, if we focus on the cap and we just analyze the stress on the left-hand side and the right-hand side of the beam section, so you will see that since the bending moments are still the same and the overall situation is the same as the case 1, so if you do the stress analysis, you'll get the same distributions. Right? This is totally the same as the case 1. We have 507 here. You have 106 here. You have 722 here, and you have 151 here. Okay. Then the Fy, so in the same way, we can calculate the average stress here. So the delta L, the sigma L, sigma R, and we can calculate the equivalent forces on the left-hand side and the right-hand side. Okay, so here just the FL. So the stresses will be the same. Let's see that. Stresses will be the same, and the average stresses on the left end and the right end will be the same as the previous example. Okay, so the FL equals sigma L by A, right? So the sigma L will be 507 plus 106 over 2. But the A will be different, right? The area will be different. Since in the previous example, in case 1, our A is here. Okay, now we're analyzing here. So in the case 1, our area is only the side flange, right? So we used 1.5 by 3.5. But in this case, the area is the whole cap. Okay, so the area will become 4.5 by 3.5. Okay. So here the area will be different. So the area will be 4.5 by 3.5, and the result will be 48.27 pound. Then the FR will be sigma R by A, so that is 722 plus 151 over 2 by 4.5 by 3.5. Then here you will get 68.75 pounds. So the delta F will be FR minus FL. That is 68.75 minus 48.27. So you get 2048 pounds. Okay. Again, we need a shear force to balance this difference. Okay. So this resultant force delta F will be pointing right. Then our shear force will be pointing left. So this shear force will be located at the interface, the green colored interface between the cap and the rib. Okay, so if you want to calculate the tau at the interface, you get a V over A interface, right? So the V will be delta F equals delta F. Then the AF, the area, in this case will be again 16 by here, right? And the dimension here is 1.5 as denoted below. Okay, so by 1.5, so you get 2048 over 16.1.5. So you get 85.3 psi. Okay, so you can see that the stress will be the same as previously, but the forces will be different because of the change of area. Okay, the area just becomes from the side flange to the overall cap. Okay. Then we can solve this problem using the other method, using the equation we just derived in case 1. Okay. So in this method, our delta F can be directly calculated from delta M by Q over I. Right, here the Q equals AD, right? And the A here is 4.5 by 3.5 as we just calculated. And the D, so what is the D value in this case? The D equals Y bar minus YI, right? Minus the Y of the area, the cap, the cross section of the cap, right? That is the overall height over 2, right? Since it's a rectangle. Okay, and so this value will be, this value is this 4.43 minus 1.75, right? So you got 2.68. Okay. So here the D will be 2.68. And the result of P of Q is 42.27 cubic inch. So here the delta F will be, since delta M equals 4700 minus 3300 by 42.27 over 346.5. So you get 2048 pound. Okay? And then you can calculate the tau using delta F over interfacial area. You get 85.3 psi. Okay, this is another solution. Okay, the other methods to solve the shear stress based on our newly derived equation.